Today's lecture is all about water. So we're going to spend some time today talking about water, what gives it its special properties, and what makes it so important for life. So we've spent some time talking about chemistry. Here's some of the stuff that you guys hopefully should know by now from looking through your textbook and from watching my lectures. We are talking about water, though. So there are three different types of covalent bonds. If you don't remember covalent bonds, go check out the last video about covalent bonds. But the long and short of covalent bonds is it's two atoms sharing electrons. Two or more atoms, I should say, sharing electrons. And you see over here with O2, these things are roughly equal. And I'm going to explain a bit more about this in a moment, but these two oxygens, they're roughly pulling on those electrons the same amount. And so you wind up with a non-polar covalent bond. Here we have a methane molecule, CH4. This is also non-polar. And I just said the reason that this one was non-polar is because those two oxygens, they're pulling on those electrons at roughly the same amount. Okay. These two oxygens want to sort of hog the electrons the same. Okay, and so there's no what's called polarity here. And CH4, carbon and hydrogen are different kinds of atoms. And so actually they are pulling on those electrons differently. Remember, these atoms are all trying to share, they're trying to get along. But this carbon and these four hydrogens, they're pulling on the electrons differently. But because the carbon is being pulled differently in all directions, it's going to still be a nonpolar covalent bond. So imagine having a four-way tug of war with one person in the middle maybe, but the four people are all of the same exact strength, right? No one's going to be able to make much progress. Water over here is different, though, because water represents a polar covalent bond. And water certainly is not the only type of molecule that is polar covalent, but it's certainly the most prevalent here on Earth. And what's happening with this is this oxygen is wanting to pull on the electrons more than these hydrogens. And if you remember the subatomic particles, you'll remember that electrons are negative, right? That's what this oxygen and these hydrogens are trying to share electrons, but the oxygen's just hogging those electrons more. Okay, and the reason for that is because of electronegativity. That's a term you should know. And all it means is that oxygen is wanting to pull those electrons more than those hydrogens. Or you could say the oxygen is more electronegative than those hydrogens. And so you get this little symbol here, this little negative symbol here. And that just means that this oxygen is more negative than those hydrogens are. Okay? And that's what gives you your polar covalent bond. And that polar covalent bond is going to give water a whole bunch of really cool properties that allow life to take place. Okay, so again, not polar covalent here, non-polar covalent because the oxygens are pulling it equally. This one's also non-polar covalent because, well, for one thing, there isn't a huge difference in electronegativity between carbon and hydrogen, but also because it's getting pulled equally in four directions. And this one over here, oxygen is way more electronegative than these hydrogens, and so it winds up with a slightly negative charge because the electrons are spending more time around that oxygen. Okay, there are numbers associated with this, but I'm not going to ask you to know them. But I will ask you to know the term electronegativity, and I want you to know why it is that water is a polar covalent bond. Why is it that oxygen has electrons spending more time around it? The easy answer is electronegativity. Okay, so the first property that, I guess it's not a property, but when you have this polar covalent bonding, you wind up getting an extra bond in here. So remember, this oxygen is negative slightly. These hydrogens are positive slightly, right? So here's a water molecule up here. Here's a water molecule here. Here's a water molecule here. So because this oxygen is slightly negative, it is attracted to this slightly positive hydrogen. Okay? And what that's going to lead to is an extra bond called a hydrogen bond. So these molecules are connected by these covalent bonds. Oxygen is connected to these hydrogen atoms through a covalent bond, a sharing of a valence electron. And then these water molecules are further attracted to each other with a hydrogen bond. Okay, there's an extra bond here, and that's going to give water some really interesting properties. So the covalent bonds along with the hydrogen bonds are really what are allowing us to be alive, basically. So what are the properties of water that allow us to live? The first one is cohesion, and that is that water sticks to itself. This also leads to surface tension. So we have this needle, you can just float a needle on top of water, and it becomes cohesive. And the reason that that's important for water to be cohesive and adhesive, meaning, so cohesive means it sticks to itself, adhesive means that other things stick to it, is because it needs to be able to get from the ground to like the highest leaves in the tops of trees. It needs to be able to be transported from the roots all the way up into the highest parts of trees. And the reason that trees are able to do that is because of cohesion and adhesion. Okay, and again, those are both properties that are resulting from those hydrogen bonds because it is a polar covalent bond. So water is also what's referred to as the universal solvent. It isn't universal, as we'll talk about in just a second, but things dissolve in it. Certain things, anyway, dissolve in it. So here we have NaCl. Somebody took some salt and they dropped it into some water. And you remember, NaCl is held together by an ionic bond. What does that mean for an ionic? What does it mean to be an ionic bond? Right? It means that this Na lost an electron, and this Cl stole that electron, and so Na and Cl are stuck together. But when you drop NaCl into water, because these oxygens are slightly negative, remember why they're slightly negative? Because they are electronegative. They're hogging those electrons from that covalent bond toward themselves. These oxygens are going to stick to the sodium. And in the same way that the oxygens are going to stick to the sodium, these hydrogens are going to stick to this chloride ion. Okay? And so because of water's polarity, it is going to dissolve anything that is polar. So oil, as we're going to learn later on this week, is not polar. Okay? And so because oil is not polar, it will just bead to the surface. It will not dissolve in water. You can kind of faux dissolve it by making something called an emulsion, but it does not dissolve in water. Water also has this weird property where it has this unusual density. And so what that means is that ice floats on top of water. And so that's kind of weird if you think about it. Usually when you make things colder, they become more and more and more dense, right? Usually when you freeze something, its density decreases. With water, the density increases when you freeze it. This is the same reason that if you accidentally freeze a soda can, that it explodes. Sometimes they explode, sometimes they don't, but it's neither here nor there. But what's happening here is those hydrogen bonds between the water molecules wind up getting locked into place. And so instead of those water molecules being able to move freely around each other, they're locked into place. Okay, so water's actually getting larger when you freeze it, because you're locking those hydrogen bonds into place. Okay, as the book explains, the lattice structure of ice makes it less dense than the freely flowing molecules of liquid water, which allows ice to float on water. The reason that's so important, by the way, is because if ice were to just fall down, think about what would happen in the coldest parts of the ocean. Ice would form, freeze, and then fall underneath. And the next layer of ice on the surface would freeze and fall underneath. And the next layer of ice on the surface would freeze and then fall underneath. And ultimately, you would just wind up with a very large frozen ocean. As it is, ice forms on top because it's colder on the surface and actually is able to insulate the water underneath it. And so ice allows our oceans to keep from freezing. Okay, they provide an insulative sort of surface to our oceans. So water actually has a very neutral pH, which we're going to learn about in lab. Distilled water's pH is about 7, which means it is neither basic, which is the high pHs, nor is it acidic, which are the low pHs. Okay, which is why your blood is, roughly the same pH as water. It's about 7-ish, because it's neutral. And we're gonna talk later on about why it might be bad to have acid running through your veins. I believe the last property that I'm going to give you for water in this lecture is its high specific heat capacity. And I put a picture of the Golden Gate Bridge here because if you've ever been to San Francisco, you should probably know that when you go there, it's generally cooler than it is further inland. I shouldn't even say cooler. If you go to San Francisco when it's freezing here, it's probably pretty reasonably nice, okay? And the reason that San Francisco is pretty reasonably nice weather most of the year is because it's right next to an ocean. Okay, so again, we're talking about water, we're talking about the specific heat capacity of water. The reason I'm yammering on about this is because water is very hard to make very hot, and it's very hard to get really cold. And so because of that high specific heat, the ocean is able to absorb lots of the temperature fluctuations in that area. Okay, we don't live near any water or any large bodies of water. And so out here in Modesto, or wherever it is that you're from, if you don't live near water, your temperatures are going to be much larger swings. So that's the reason it gets up to the, well over the triple digits in Modesto, and the reason it gets down to below freezing in Modesto. Whereas San Francisco, average temperatures are probably about, 62 degrees Fahrenheit year round. Okay, so the next thing that we're going to be learning about, the next lecture, is going to be about biomolecules. Now that we've been able to learn about all these different kinds of chemical bonds and things going on with these, we're going to get, hopefully, we're going to get back to biology and away from chemistry so we can learn about these 4 biological macromolecules, or 4 biomolecules.